anything but slow. The cells are rapidly producing necessary material for eventual binary fission. They're cooling up. They're producing enzymes, they're transport proteins that will allow them to grow in this new environment, if it is a new environment. And if it's not a new environment, then typically it'll be a very slow or very, very short lasting phase. Eventually, however, these cells begin to enter into binary fission, and then we're off into the next phase, and that's what we call the log or the exponential phase. Some of the older literature may still refer to it as the geometric phase. I think exponential is probably more common, and I tried to avoid long, so you're more confused with the lag. So, the exponential. It is a period of exponential growth, and your book talks about the difference between exponential and arithmetic growth. This is why we have to use logarithmic scales when we're talking about bacterial growth. When we plot it, we utilize semi-log paper, semi-log scale. The y-axis is a logarithmic scale, the x-axis is a linear. Notice, and I still find students that while I say it's logarithmic, you still don't realize what I'm talking about. This is 10 to the second, 10 to the fourth. This is 100, 10,000, a million, 100 million. 10 to the 10th would probably be, what, 10 billion. Large numbers of organisms. So if you had a arithmetic scale, you could begin to get it all along there. It would be up over there and out on the street. Okay. The idea I'm trying to develop here is that line that we call the exponential growth curve has a slope. That slope is defined by rising or this is just a mathematical term. And that line, the slope of that line, is a reflection of the amount of growth that's going on in that population, which is a reflection of the amount of the energy metabolism going on. Metabolism can be influenced by several different things. And we're going to have several, several of them at the end of this not today, but later on. We've seen, what are some of the things that we've already seen on that table that would influence generation time? Temperature, an environmental cue, environment, the temperature, the presence or absence of oxygen. Some organisms require carbon dioxide for growth, so the presence or absence of carbon dioxide. Even the amount of carbon dioxide, the amount of oxygen can influence the shape of that curve. The pH. There are some bacteria that will grow like that, but only if the pH is 2. No, 2. Various things. Environment. So, other things that would influence that curve. In addition to the environment, the medium itself. How many goodies can you give them in order to grow? How much metabolism, how much work do they have to do to make what they want? If they have to work for it, then the lag phase is going to be longer. Our log phase is not going to be at the same shape. Now there's a mathematical expression that defines this, and I gave you that equation. There is, now that equation does not define that line. That equation relates the numbers of organisms with their generation, numbers of generations. That line is defined by what we call the growth rate constant, and it's called the K-value. The K-value, the growth rate constant. It has the units of generations per time. Generations per time. Okay, now we have 4 different slopes, 4 different K-values. In which of these lines, which of these cultures, A, B, C, or D, would the organism have the shortest generation time? forget that the slope of this is indicative of the number of binary changes undergoing per unit of time. And the smaller the generation time, the more rapidly the population is deployed. Which of these lines, let's say here, let's say this is B. Which, I'd like to use some terms that you're not familiar with yet, so we can't really do that. Well, let's do it. Let's suppose that we've got this population back here going to B. Which of these curves, A or C, would be reflective of that same population, but growing in a poorer medium? Poorer medium. C. Right. Longer generation time, the slope doesn't. Okay. We talked about the factors that can be influenced by it. It can be indicative of genus and species. And again now, we talked about Streptococcus and E. coli, and we saw widely different generation time, growing in the same medium at the same temperature. And we worked it out that this is simply a reflection of the rate of metabolism, the rate at which it produces ATP. Those cells that are capable of producing ATP more rapidly will have a shorter generation time. That can be influenced by the nutrients and by the environment. So we can have one curve here for E. coli, and we can have another curve that's drastically different for E. coli, the same E. coli, if we don't maintain the same conditions of nutrient and environment. Okay, now, we see our cells coming out of lag phase here. And one by one, they all begin at some point, they begin to undergo binary fission. But ultimately, where they're up here into what's referred to as the toe of the long phase, of the exponential phase. At that point in time, and all the way up through here for a certain period of time, the culture is said to be in balanced growth. Balanced growth. Now, what does that term balance mean to you? Where are you from? Have you ever heard the term balanced growth? What does that mean? Balanced growth.
I'm sorry, where did you say that balance?
Well, typically, once all the cells are into the exponential phase, then it depends upon the organism. I don't know what you call it at the inflection point here.
Okay.
Somewhere right about in there, it looks like it's starting to curve off. Okay? Now that will vary with different organisms. For our example, we say it's in balanced growth. What is balance? What does the term balance mean to you? Jen, what's balance mean? You're balanced. What's that mean? Okay. You're balanced, or a triple B balance. Okay, what it simply means is that at this point in time, the cells that comprise that population are all multiplying. They're all metabolizing at as fast a rate as the conditions will allow. They are not producing anything in excess. They're not storing anything. As fast as they make ATP, they use it. It's balanced. As soon as they produce materials that they need for other pathways, they're off to those other pathways. Balanced growth. Balanced growth involves the production of what is typically referred to as primary metabolism. Primary metabolism. Now, this is the region that I've indicated balanced growth. And again, this could be a little bit farther down or a little bit farther up, depending upon the organism. Primary metabolite. First off, what is a metabolite? You've heard that. Metabolism. That's a reflection of the word metabolite. What is metabolite? Well, they're things that the cell produces. Things that the cell produces as a consequence of its growth. Now, a primary metabolite is one of those things, or those things that the cell needs to continue to grow. They're required for growth. Vitamins, making things and using them as rapidly as it makes them. This is the phase that we could typically think of the production of primary metabolites. Citric acid. Citric acid is the primary metabolite. Where would we find citric acid in the metabolism? There's a cycle name for it, citric acid cycle, TCA cycle. Okay. We're going to come back to that. At some point, however, that population will begin to slow down. Now, you say, well, it's not slowing down. Yeah, you can't see it on that curve, but it's starting to sense that the cupboard may be getting bare. And it will then go into what we call unbalanced growth. And that's typically the rest of the exponential growth curve. Now, why would a population that is growing real well, now remember, this is in a closed system, this is a batch culture. Why would a population of cells that are doing so well start to slow down? And they may not even slow down perceptibly to reflect it in the growth curve, but we might see using some type of a marker, we see, well, it's not making fat as rapidly as it would earlier. It's slowing down. Say it again. We typically think they run out of required materials, maybe oxygen, it may be a nutrient. Now, nutrients are metabolites. Nutrients are something we give them that they have to have. I won't say that they run out of primary metabolites, but as they run out of nutrients, then they start to get primary. So they may begin to deplete the medium of the materials that they need for growth. For example, maybe growing on the glucose-based medium, it starts the concentration of glucose gets pretty low. So it begins to adjust itself. What else? What else is a reason why you begin to slow down? Closed system. Yeah, you're getting there. You're getting there. What's the other more obvious one? Right. In other words, as it builds up toxic waste products, they don't go anywhere, and they may become toxic. Lactic acid. Many bacteria produce lactic acid as a primary metabolite. But that lactic acid, if it can't be neutralized or removed, that lactic acid will serve to limit its further growth. It becomes a limiting material. So it builds up waste products. And for years, ever since we knew about a growth curve, up to about 8 to 10 years ago, we thought, this is why this population will not continue in that long growth. Simply because of the fact that it is either or, maybe both, depleting the culture of required nutrients, and it is accumulating toxic byproducts. Well, that's not nearly. Brooke mentioned, what did you say? Not enough room. In other words, there's evidence now that bacterial cells can sense their population concentration. And they do so by a process known as quorum sensing. Quorum sensing. This was first discovered in bacteria. It's been shown to exist in all types of cells. Quorum sensing. Now, what is it? Quorum sensing is the ability of the cell to regulate